Okay, one thing that we did not cover in Calculus 1 was a type of function called the exponential function. And so that's where I want us to go now, is to talk about the exponential functions and what ultimately what, well, we'll get into the derivative. First of all, what do we mean by an exponential function? And in general, basic exponential function is just some number to a power, right? We did not talk about where the power was the variable. We talked about x to a power rule, but power rule is not going to work on this because x is the power, and it's not a power rule, unfortunately. That'd be neat if it was, but it's not, okay? Unfortunately, it is not. Now, we can get a little bit of information out of the definition, and that's why I mentioned earlier about recall what the definition of derivative is. And so the derivative here, definition-wise, here's what this tells us. We have the limit as h approaches 0, well, it's f of x plus h minus f of x over h. And so that, if you plug in x plus h for x, you have the limit as h approaches 0. It would be a to the x plus h minus a to the x over h. and that's, we did not do limits of that sort either. It's complicated, I guess, but not too bad. But here's what we can do. Actually, it turns out a to the x plus h we can write this way. See what I did there? I just wrote a to the x plus h times a to the x as a to the x times a to the h. Isn't that? Usually we go this way with it where we add the exponents, but we can break it back up if we want to. And the reason you do that is because notice then I've got a factor of a to the x. So I can factor that off. So if I factor a to the x off, that leaves me a to the h and then minus 1. Kind of a placeholder there. And then the good news is h is going to 0, so that a to the x is a constant, and so I can bring it out outside of the limit because this is not affected by the h going to 0, so I can just bring it out. Okay. Now, we'll say more about this later, but the nice thing about this is this derivative turns out to be that. And so notice one thing about the derivative of a to the x is in part of the derivative. So the derivative of a to the x, or a number to the x power, part of it is itself. That's interesting because we've never had that happen. But part of the derivative of a to the x is a to the x. Now this other part, what I'll say about that is that just turns out to be a constant, a number. And after we do something more in just a second later, I'll say more about that, what that is. But basically, the derivative of a to the x is itself times a constant. That's what we can. That's what we'll say right now, okay? And it varies, like for, whoops, f of x equals 2 to the x, the derivative. And you can do it, plug in the 2 here, 2 to the h, and do a table. Remember doing those? I'm not going to make you do those, but we did it that way. But what we can say right now is it's 2 to the x times a constant, and it turns out that constant's about approximately 0.69. There's a more precise one, but value for that. But But yeah, if you did like a table, put a 2 in there and then do the limit as h, you get about 0.69 approximately. For 3, it's about 1.10. But there is good news on that. There is a more specific value for that, and we'll talk about that in just a second. Okay, now here's some really good news. If it turns out there's this base, A here is the base, so depending on your base, that determines your constant there. But if the base is base E, the number E, have you ever worked with that much? Base E? We do a little bit of that in some of the algebra, but E is just, it's a constant like pi, right? 2.71828. It's, it looks like the way it starts is it just repeats 1828, but the next one's 459. So it's like pi, it's an irrational number. It doesn't repeat or terminate. But what I was going to say was, if it turns out that this number, actually the definition, or one way to define it, is E is the number for which that, we had, what was it, f prime of x was raised to a to the x times limit. H approaches 0, a to the h minus 1 over h. One way to define E is the base that makes this 1. This limit of a to the h minus 1 makes that value 1. So in other words, E, the limit as h approaches 0 of e to the h minus 1 over h is 1. So this part of my exponential derivative, that part is 1. So do you notice what that means? So if we've got f of x equals e to the x, the derivative is, well, it's e to the x times this limit of e to the h minus 1, but e to the h minus 1 over h is 1. If f of x equals e to the x, the derivative is e to the x. E to the x is its own derivative. Pretty interesting little function, because what other function can you say that about? I don't think there's any. E to the x is its own derivative. So it's pretty nice. So they have some in this section here. Okay, so what if I've got, so what about f of x equals x cubed times e to the x? Well, the derivative of that, well, you got the product rule. 3x squared times e to the x. And then reverse that, so we've got x cubed times the derivative of e to the x, but the derivative of e to the x is e to the x. So run into stuff like that. What about f of x equals e to the 5x squared? So what if we have, what if we don't have the power being x? In this case, it's 5x squared. E to the 5x squared. Well, what rule is going to kick in there? Chain rule. It's a chain rule. The e to the 5x squared, it's not the most obvious chain rule, I guess, because you don't have the inside and outside, obviously, going there, but the power is the inside. The base is the outside. So with that in mind, what's the derivative of the outside? Well, it's e to a power. e to a power, the derivative is e to the power, yeah. But since it's a chain rule, I also have to do the derivative of the power, right? So what would that be? Derivative of 5x squared, 10x. With me there? So if you've got something e to a power other than just x, it's e to that power times the derivative of the power, because it's a chain rule. Yeah, this one had some interesting things that happened. Let me get it too. Okay, so we've got y equals e to the minus w over e to the w plus 1. Quotient rule, of course, is what we're going to do. So low d high minus high d low over low squared. So low e to the w plus 1 times the derivative of e to the minus w. Well, that's kind of like the one we just did. E to the minus w, well, the derivative is itself. But since the top is not just w, I also have to do the derivative of the power. So that would be, what would be the derivative of the power? Negative 1. So it's e to the w plus 1 times e to the minus w times negative 1. Switch those up. So that's low d high minus high, e to the minus w times the low, okay? So what's the derivative of the low? The derivative of e to the w is e to the w itself. And then the derivative of 1 is 0, so it's just e to the w. Then over low squared. I think this one is just a matter of, yeah, a lot of stuff in these to get down to the answer. You have to really know some algebra stuff, so might have to review some things along the way. But here, that's just minus e to the minus w. So I just need to distribute that. And when I do that, okay, so it's minus, I've got minus e to the minus w times e to the w. And so what do we get there? E to the minus w times e to the w.
To the 0.
Yeah, remember that's where we just kind of did that in reverse. That's where you add those exponents. So you wind up with minus e to the 0, which is minus 1. Anything to the 0 power is 1. So that times that's 1, and then that times that, of course, is just minus e to the minus w. And then we have the same sort of thing here, don't we? That's e to the 0, which is 1. And then, lo and behold, uh-oh, it doesn't cancel, it's minus 2. So there's probably some other things we can do, but you get the idea. All right. Now we said we're going to do derivatives of exponentials, but hey, let's throw in an integral here too. And the good thing about an integral of e to the x, well, I mean, the good thing about this one is it's easy. Since the derivative of e to the x is e to the x, the integral of e to the x dx would be e to the x plus c, yeah? I mean, if you have a power other than x, of course you've got to think through that. This one we can do with the substitution, can't we? Just I like to call these simple substitution. They'll come up all the time in this course, so be ready. But yeah, e to the 2x. To get this done, we just do a u substitution. U equals the power 2x, and then du would be the derivative of 2x, which is 2 times dx, and so divide by 2, and that's my dx. So we wind up with e to the u times du over 2. So that's why, you see, I call them kind of simple substitution, because really all it amounts to is we have a factor of a half there that we didn't have in the previous one. You see what I'm saying? Well, it's 1/2 e to the u. That's 1/2 e to the u, isn't it? Antiderivative. Let's see, and then just change back the u to 2x. Yes? Okay. Okay, now, let's talk about derivatives of logarithmic functions. And maybe a little rusty on the logarithmic functions, but just know, first of all, logarithmic functions are the inverse function of an exponential function. Yeah, if I've got log base a of x equals some number y, the reason it's called the inverse function is because that statement right there, that expression right there, equation, the exponential